Hello, and I hope everyone is having a good day today. So today, and I hope you like my pictures, we're going to be talking about energy. What is energy? Well, energy is the ability to do work according to Wikipedia. What is work, you may ask me? Well, according to Wikipedia, work is the use of energy. I misspelled use. Work is the use of energy. And unfortunately for us, that's a very cyclical reasoning. It's cycle, right? Energy is the ability to do work. Work is the use of energy. That doesn't really tell us what energy is. And in this year, we're going to be learning a lot about energy of reactions. So it's good for us to kind of understand, have a working definition, a better working definition than just work and energy. So I'm going to kind of simplify it for you. Really, energy is the ability to do. To do what? Well, to do anything, right? If you don't have any energy, you can't do things. And if you want to do something, you have to use off energy, right? And there are a couple examples of things you can do with energy. You can give off heat. You can move an object. We call that a force. And you can emit photons. You can emit light, right? And these are all examples of, well, different things you can do with energy. When it comes to work, work is specifically about force. So when you move something or something is moved, that's work, right? So energy is really the ability to do most anything. The only way, unfortunately, to measure energy, though, is comparing a change in a situation. That's really what it is. To understand energy, you have to look at the change in which that situation went about. So let's look at an example of what I mean. Gravity pulls matter together. So gravity, it pulls objects on Earth. Gravity pulls us towards the center of mass. That's what it does, right? And there's energy related to that gravity. So this is my cat, Gus Gus. This is an animation of him. Let's say he's on a mountain. If he wanted to increase his potential energy, gravitational potential energy, where does he move? In other words, if he wanted to be able to have gravity give him more energy, where is he going to move? Right now, gravity's not really going to do anything to him because he's kind of chilling on the ground. But if he goes up the mountain, gravity will be able to do more to him. So he now has increased his amount of energy, right? He increased the potential for that gravity to move him, right? And as we talked before, where on the mountain will he have zero gravity? Well, that's zero gravitational energy. Well, that's at the bottom where the gravity is not going to move him anymore, not going to cause a force, right? So that's what I mean by looking at a change. We can only tell that Gus Gus increased his potential energy because he moved up the mountain. It's hard to look at a situation and say that right there in that instant has this much energy without something to compare it to. Let's look at that in terms of chemistry and ions. So here we have two ions. We know that these two ions are going to attract each other. What we're going to say is that at rest, nothing's happening. So we're going to just say there's zero energy. Now, I understand that there is an attraction, and the attraction is keeping them together. But just like we can say that if you're just standing on Earth, the gravity's not doing anything, we're going to say that that is the maximum attraction between these two particles. They're not going to move anymore. So we're going to say that's zero. If I were to pull these particles further apart, obviously pulling means that I had to give energy to the sphere. The sphere just gained energy. So the overall change in the energy of this system must be greater than zero. It has to increase. We had to put energy to pull it apart, right? So that would be a increase in energy. Whereas if I were to let those spheres go back together, the spheres must have lost that energy that I put in the first place. So that's a negative change in energy. And by negative, I mean from here to there. That's a negative change in energy. Now, overall, those two changes, when you add the amount of energy that we gained and lost, overall, that would be a change of zero, right? But each individual change we're either increasing the amount of energy or decreasing the amount of energy. Now, I know I put a delta sign, that triangle, which means changing, but because energy has to be measured with a change, instead of saying change of energy, we can also just say energy. When energy is positive, that means you've gained energy. When energy is a negative number, that means you've lost energy. It's just like money. When your money is positive, you went from zero money to more. If money is negative, you went from zero money to less, right? So sometimes we put energy with a delta, sometimes we don't. Specifically, since we're talking about ions, ionic bonds. We know that bonds are strong forces of attraction, right? And we were just seeing what happens when we weaken or strengthen bonds. And we saw that breaking bonds, when we pull them away, breaking bonds requires energy to be added. You have to add energy into the ions to pull them apart. And therefore, if you have to add energy in the ions to pull them apart, the opposite must be true, that when you make a bond, you actually release energy. The energy is released. There's a negative amount of energy, which actually is good. We'll talk about that in a minute. Ionic bonds, as we said, all ionic bonds are electrostatic attraction between oppositely charged particles. And ionic compounds form a regular three-dimensional structure. You never really find, if you were to look at NaCl, you wouldn't find just one Na ion and one Cl ion. There's no actual structure that just has two ions. It actually looks more like this. So this is the whole, this would be a solid structure of really most ionic compounds. And we can see that in this one, each cation will be attracted to 6 anions around it. You can't, it's hard to see, but if you see on the surface, you see that one purple cation would have 4 green anions, one above, one below, one left, and one right. In 3 dimensions, remember, in the middle of those, there's also one in front and one in back. That's where the 6 is coming in. But not only that, each anion is attracted to the 6 cations around it. So we see that in this structure, there's a lot of attraction. All of these attractions. So even though we say that the chemical formula of NaCl is 1 Na to 1 Cl, that's not actually what's going on. It's actually, according to this, 6 Nas are being attracted. For each Na, there are 6 bonds to a Cl, and for each Cl, there are 6 bonds to an Na, right? There are all these bonds. But what we're doing is we're giving the reduced whole number ratio. That's how we report ionic compounds. The solid structure of any ionic compound is called an ionic crystal lattice, or just a crystal lattice structure. And it's really important to talk about the crystal lattice structure, because the crystal lattice structure tells us about all different properties of ionic compounds. Now, just to show you what was going on, this is what I meant, that there's all this attraction and repulsion. And that's how we get the different shapes. And there's actually more than just that one shape I just showed you of ionic crystal lattices. There are 3 of them, and it all has to do with the amount of attraction to repulsion and the size of the ions. And they're all interacting. There's going to be one set distance. Now, here's the weird thing. We talked about bonds breaking. And when a bond breaks, to break a bond, you need to add energy. And when you make a bond, energy is released. But there's something a little bit more, an extra type of energy that goes in the formation of a solid ionic crystal lattice. And that has to do with something called lattice energy, the energy of the actual shape of that solid, the lattice. So lattice energy is defined as the energy required to completely separate a mole of solid ionic compounds from its crystalline structure into gaseous forms. Now, look at this. We talked about the idea that we're calling lattice energy completely separating them. And look at that. Our delta H, our energy is actually greater. Our energy is going up. And that makes sense because we're breaking up all of those attractions in there, right? So let me make this very clear that this has to do with the fact that basically lattice energy is the idea of going from a gaseous, all these gaseous ions into the crystal lattice structure. Now, unfortunately, and this is going to be super hard or super confusing, some define it as going from the separation of a solid ionic compound into gaseous ions, and some define it as the opposite. In reality, the lattice energy is just related to the amount of energy that is associated with the formation of that crystal lattice structure. And the only difference between the two definitions is the value of delta H, or the value of the energy. Sorry, delta H is energy. And all that means is that if we're talking about a positive amount of energy, that's how much energy it takes to break the crystal lattice. If we're talking about the negative energy, that's how much energy it takes to make the crystal lattice. So I showed here an example of, up here, the numbers show an example of breaking it. Down there, I showed you a schematic of kind of making it. And we're actually going to see numbers to make it. Is that true? Yes. The more energy something takes, the more so the more energy a task takes, the more difficult it is. And we know that difficult things are harder. We tend to, in nature, if nature goes the way it is, difficult things don't occur. Why am I relating that? Well, if it takes a lot of energy to break up a crystal lattice, that tells us that that crystal lattice is very, very stable. It's hard to change it, right? The more energy it takes, the harder it is to change something. Okay, so how do we come up with lattice energy, and what does it all have to do? Because it seems like it's just the bonds, but it's a little bit more than just the bonds. Remember that for any ionic compound, I'm sorry, how do we calculate lattice energy? I'll get back to what I was saying before. So lattice energy is this equation where Q1 is the charge of one ion, Q2 is the charge of the other ion, D is the distance between the centers of the two ions, and K is a constant that I gave you, even though you didn't need to know. And that's how much energy is involved in those two, right? And we know that if Q1 is a positive and Q2 is a negative, we can see that the energy is going to be negative. Negative usually refers to attractive energy. Hey, look, that's Coulomb's law. That's right. I didn't just teach you Coulomb's law for fun, but I taught you Coulomb's law because it shows up and up and up. And we can see a couple of cool things here that if you have a giant lattice energy, meaning if it takes a lot to break something or make something, right? It's going to be more stable. And we can even look at Q1 and Q2 values, that the higher the values of Q1 and Q2, higher the absolute values of Q1 and Q2, the higher the absolute value of energy. In other words, the higher the charges of Q1 and Q2, if Q1 is a +3 and Q2 is a -3, that's going to have a much greater lattice energy than a Q +1 and a -1 charge, right? Also the distances. So in general, smaller ions tend to have higher lattice energies, right? So to make a very stable lattice, you want something with high charge but low radius, or atomic radius, ionic radius, sorry. Okay, so let's talk about, we're going to now move on to exactly what lattice energy is. And this is why I was saying it's confusing. So if the overall reaction to take a sodium and half of a chlorine molecule and turn it into a sodium chloride, if that's the overall reaction, then this is actually a thing that we calculated, we measured, we know how much energy it takes to melt sodium into gas. It takes 108 kilojoules, right? And that's a positive amount because we have to add energy to the sodium solid. We also know how much it takes to turn a sodium atom into a sodium ion. That's just ionization energy. And we also know how much it takes to turn a chlorine atom, half of a chlorine molecule, into a chlorine atom. That is bond energy. We're breaking up the bond between those Cl atoms. And we know how much energy it takes to turn a Cl atom into a Cl ion. That's electron affinity. But here's the weird thing. We calculated all these individual ones in one type of reaction. However, there's a separate type of reaction that will directly tell us how much energy it takes to go from NaCl solid into its individual elements, right? And if we look at the total math there, well, we can see that to go from individual elements into its solid, that's negative 411 kilojoules. If you do the math here, you will notice that we're way off. We're losing a lot, right? I mean, if we look at just the amount it takes for sodium to become ionized, that's already greater. So the law of conservation of energy is broken here. That didn't make any sense, right? So that's where this idea of lattice energy came in, that even though we know how much energy it takes to turn sodium into a gas at room temperature, turn sodium gas into ions at room temperature, break up those chlorine molecules at room temperature, turn those chlorine molecules into ions at room temperature, even though we know all that, just adding them all up, it, it's not enough to just add them all up. It's not enough to do that. That won't actually create our crystal lattice structure. It's not until we put in our last value of lattice energy that we can determine that our last value of lattice energy, that mathematically this all makes sense. In conclusion, to summarize, what I'm saying is that it takes energy not just to break up ionic bonds, but to actually form that special, specific arrangement in the crystal lattice. And that's what lattice energy is. And I think that's going to be it. Yep, that's it for today. I hope everyone has a wonderful day. And if I can figure out how to do it, bye.